Linear scattering losses. This is another kind of loss mechanism takes place inside the fiber. Linear scattering mechanism cause the transfer of some or all of the optical power contained within one propagating mode to be transferred linearly, which is proportionally to the mode power, into a different mode. So this process tends to result in attenuation of the transmitted light, as the transfer may be to a leaky or radiation mode which does not continue to propagate within the fiber core but is radiated from the fiber. Linear scattering may be categorized into two major types. One is the Rayleigh scattering and another is the Mie scattering. Both result from the non-ideal physical properties of manufactured fiber, which are difficult and in certain cases impossible to eradicate at present. Just consider this situation. We have a fiber and this is the core, and this part are the cladding, right? Now suppose the light is moving from this point to in this direction rather. Okay, within the fiber we have some local inhomogeneity where the refractive index of this portion, this small portion, is slightly different from rest of the core or cladding. Okay, so these are the local inhomogeneities. Now what happens? Light should follow this path, right? If there was no inhomogeneity, it should move in this direction, and then it will have a it would have a total internal reflection and it will come back to the core. But because of this local inhomogeneity, light will change its direction, and it may happen that the incident angle becomes different, and the condition for total internal reflection is now invalid, and instead of total internal reflection we have refraction of the signal or refraction of the light wave inside the cladding. So this particular wave, this particular portion of the wave is lost. It will never come back to the core. Now consider the Rayleigh scattering. So Rayleigh scattering is the dominant kind of intrinsic loss mechanism in the low absorption window between the ultraviolet and infrared absorption tails. It results from inhomogeneities of a random nature occurring on a small scale compared with the wavelength of the light. These inhomogeneities manifest themselves as refractive index fluctuation and arise from density and compositional variations which are frozen into the glass lattice on cooling. The subsequent scattering due to the density fluctuations, which is in almost all directions, produces an attenuation proportional to 1 by lambda to the power 4 following the Rayleigh scattering formula or Rayleigh relation. Now let us see the absorption characteristics of OH group again, and you can see that we have a first window right here. Right here we have a first window. We have a second window right here. It was previously used for long haul communication, that is 1300 nanometer region, and this is the third window that is used right now. We are using this window around 1550 nanometer, and here we have the peak of the absorption or attenuation. This is due to the hydroxyl ion. So consider the Rayleigh. If we add with this previous figure, if we add the Rayleigh scattering model, so this is the way the Rayleigh scattering attenuation changes with the wavelength, right? So this is the actually contribution due to the Rayleigh scattering. So this is for the standard fiber, and we have more or less 0.2 dB per kilometer loss near this region. We have another kind of scattering that is called the Mie scattering. Linear scattering may also occur at non-homogeneities which are comparable in size with the guided wavelength. These result uh, from the imperfect cylindrical structure of the waveguide and may be caused by fiber imperfections such as irregularities in the core cladding interface, core cladding refractive index differences along the fiber length, diameter fluctuations, strains, and bubbles. When the scattering inhomogeneity size is greater than lambda by 10, where lambda is the wavelength, the scattered intensity, which has an angular dependence, can be very large. The scattering created by such inhomogeneities is mainly in the forward direction and is called me-scattering. Depending upon the fiber material, design, and manufacture, me-scattering can cause significant losses. Though this me-scattering is not the dominant one, Rayleigh scattering is the dominant kind of scattering loss. Along with linear scattering losses, we have some kind of nonlinear scattering losses as well. Optical waveguides do not always behave as completely linear channels whose increase in output optical power is directly proportional to the input optical power. Several nonlinear effects occur, which in the case of scattering cause disproportionate attenuation, usually at high optical power levels. This nonlinear scattering causes the optical power from one mode to be transferred in either the forward or backward direction to the same or other modes at the different frequencies. The most important types of nonlinear scattering within optical fibers are stimulated Bruglia and Raman scattering, both of which are usually only observed at high optical power densities in long single mode fibers. This scattering mechanism in fact give optical gain but with a shift in frequency, thus contributing to attenuation for light transmission at a specific wavelength.